In one of my other videos, I was talking about how when you're doing a t-test, you're using a curve that would exist in a situation when the null hypothesis is true. And I was thinking that it might not have been completely clear what that means, so I wanted to make another short video to help explain that concept a little bit more. We could be doing a one-sample t-test to test if the mean of a population equals 23. If we're testing whether the mean of a population equals 23, our null hypothesis will say that the mean does equal that value. And this value of 23 in our null hypothesis will be called the null value. The null value is just the value that's being tested in the one-sample t-test. It's being tested for the population mean. And in the one-sample t-test, we're going to collect data from a sample of the population that we're interested in, and we're going to record data values from the sample and calculate the mean of our sample. And then we're going to also later calculate a t-score, and we'll be able to decide if the population mean appears to be 23. And if we've collected data from a normal population, or if our sample size is 30 or higher, we know that the curve that goes around the means of the possible samples that might be selected is a bell curve. If we've sampled from a normal population, meaning the population we're studying is normal, or if we've collected data from at least 30 people, the means of the set of possible samples that could be selected in the one-sample t-test will have a normal curve outlining them. So if we know that one of those two things are true, we know that the curve around the possible sample means, or the curve around the means of the possible samples, is a bell shape. And the center of that curve is whatever the population mean actually equals. But we're testing whether the population mean equals 23, so we actually don't know what the center value is. We don't know what the population mean equals. If the population mean actually does equal 23, then our bell curve of possible samples will be centered at 23, and the highest stack of possible samples will be at 23, and the stacks of possible samples will be shorter once you get further away from 23 at both ends, meaning you'll have fewer and fewer possible samples that will give you a mean further away from 23. So if the population mean really does equal 23, you're unlikely to get a sample with a mean far at the left end down here, or a sample with a mean far at the right end up here. What if the population mean doesn't equal 23, and it actually equals something else like 25? If that's true, then the highest peak the peak of your curve will be at 25, and the curve will get shorter further away from 25, meaning if the population mean does equal 25, fewer and fewer of the possible samples will give you a mean further away from 25. When you go further away from 25 toward the left end, there are fewer possible samples that will give you a mean far at the left end of 25, and there's fewer and fewer possible samples once you start to go to the right end further above 25. up here. If the population mean equals 27, the curve peaks at 27, and once you start to look at numbers far to the left of 27, there aren't that many possible samples that will give you a mean down here, meaning there aren't that many possible samples that will give you a mean far to the left of 27 or far below 27, and there aren't that many possible samples that will give you a mean far above 27, because most of the possible samples are near the population mean in the center, especially when the possible samples have this bell shape. So when the population mean is 23, most of your possible samples will have means near 23. When the population mean equals 25, most of your possible samples will have a mean near 25. And when the population mean equals 27, most of the possible samples will have a mean near 27. So one of these is the situation when the null hypothesis is true, and it's this first one right here. This is the situation in which the population mean equals 23, which is where the null value is at the center. And what we'll be using, what you use for the t-test is the curve that goes around, the curve that's centered at the null value, which is the value that you're testing. Let's say we collect a sample and the mean of our sample ends up being 26. In the situation where the null hypothesis is true and our curve of possible samples is centered at 23, 26 looks like an extreme outcome. But if another situation is true, such as if the population mean really equals 25, now it looks like 26 isn't such an extreme outcome anymore. It looks like it would actually be fairly easy to get a sample mean of 26 in a situation where the population mean equals 25. And if the population mean equals 27, in this curve it looks like it's not that difficult to get a mean of 26 in your sample because it doesn't look very extreme. It's not very far away from 27. What we need to do in the one sample t-test is calculate how extreme our sample mean of 26 is in this situation where the population mean equals 23 and the null hypothesis is true. And you might be thinking, why can't we just look at our sample mean of 26 and compare it to 23 and then decide how extreme it is based on how far away it is from 23. But the reason we can't do that is because even if we know that this curve is bell-shaped, we don't know how far it extends. We don't know meaning we don't know the spread of the curve. It could be that the curve is centered at 23, but the curve actually is fairly high at 26, and it doesn't get low until 28. So we don't know how fast this curve is dropping down, like this. So the only way we can calculate exactly how extreme 26 is in this situation is if we calculate a t-score for our sample mean. And we have to use the formula for the t-score of a one sample t-test. What this formula will give us for a t-score is the number of estimated standard errors between the null value, the population mean that we're testing, and the mean of the sample that we found at 26. The t-score tells us how many estimated standard errors fit between the null value and our sample with a mean of 26. And if the t-score is high, comes out to a high number, it means that we did end up with an extreme outcome in the situation where the null is true. Gotta wait for my dog to stop barking. If the t-score comes out to a high number, it means that our outcome of 26 is in a small piece of the curve up here. It means that the curve is dropping down. What I mean is, if the t-score comes out to a high number, it means that 26 is inside a really small wedge of the curve at the extreme end, like it is in this picture. If the t-score didn't come out to a high number, it would mean that the curve is extending further, and that 26 is actually still at a high part of the curve. That would be if the t-score came out to a low number. So basically, the t-score tells us how extreme our sample is in the situation where the null is true. And if the t-score comes out to equal to or above the critical value, it means that our sample is extreme enough to reject the null hypothesis that the population mean equals 23. If it reaches the critical value, it means that this outcome, this mean of 26, is so unlikely in this situation where the null is true that we can reject the idea that this situation right here is true, meaning we can reject that the population mean equals 23, and we can decide that the population mean actually equals a different value. And when we decide that the population mean equals a different value, what actually happens is our sample becomes more believable, because if we decide that the population mean isn't 23, and we decide it's actually, meaning we reject the null hypothesis, and we decide that the population mean is somewhere closer to our sample out here. For example, if we decide that the population mean is somewhere up here, and that the curve is centered somewhere up here, our sample of 26 isn't in an extreme end of the curve anymore, and it becomes more believable. And that's basically what happens when you reject the null hypothesis. When you reject the idea that the curve is centered at the value that you're testing, your outcome changes from a less believable outcome or a less likely outcome to a more likely outcome, and your outcome is better explained. That's the logic. So that's how a one-sample t-test works. What about an independent samples t-test? In an independent samples t-test, you're trying to decide if two population means are equal, meaning you're trying to decide if the mean of one population is the same as the mean of another population. And what you have Well, what you do in an independent samples t-test is you select a sample from population 1, and you select a sample from population 2, and you calculate the means of your two samples. And if you subtract the mean of your first sample by the mean of your second sample, you get a sample mean difference. Your data set has a sample mean difference. And this curve is meant to show the sample mean differences of the possible samples that could be selected. And if both populations that you're studying are normal, or if you've collected data from at least 30 people in both samples, the curve that goes around the sample mean differences, the curve that outlines the sample mean differences of the possible samples is a bell shape or a normal curve, like it is here. So you can know what the curve is that's outlining the sample mean differences. You can know that it's bell shaped if you know that the populations are normal, or if you know that both of your samples have at least 30 people. But just like in a one sample t-test, you don't know what the center value equals. You don't know where this bell-shaped curve is centered at. And the center value depends on the difference between the two population means. If the means of the two populations are equal, meaning there's a zero difference between the two population means, your curve will be centered at 0, meaning if there's a zero difference between the two population means, you're less and less likely to collect a data set with a sample mean difference far from 0, further away from 0. So the sample mean difference is whatever the difference between the two sample means is. If your first sample mean is 4 and the second one is 2, your difference comes out 2. If the mean of your first sample is, so that outcome would be up here. If the mean of your first sample is 2 and the mean of your second sample is 4, your sample mean difference is -2. Which would be an outcome out here. So in this situation, where the null hypothesis is true in an independent samples t-test, the curve of the sample mean differences peaks at 0. If the difference between the two population means equals 2, meaning if the mean of the first population is 4 and the mean of the second population is 2, the difference between the two population means is 2 when you subtract them. If the difference between the two population means is 2, then the curve of the possible samples peaks at 2. And it's harder or more difficult to get a data set with a sample mean difference far below 2 or far above 2. If the difference between the two population means is 4, for example, if the first population had a mean of 5 and the second population had a mean of 1, the difference between the two population means would be 4. And in this situation, if this is true, then the curve of your possible samples peaks at 4, and there's fewer and fewer possible combinations that have sample mean differences far away from 4, meaning when you look at this, there aren't that many data sets that will give you a sample mean difference. There aren't very many combinations of participants available that will give you a sample mean difference far below 4 or far above 4 in this situation right here, where the difference between the two population means is 4 and the curve peaks at 4. So if we look at the situation where the null hypothesis is true, which means a situation where there's a 0 difference between the two population means, then we're looking at this situation where the curve peaks at 0, because the null hypothesis in an independent sample t-test says the population means are equal, and there's a 0 difference between them. So this is the situation where the null hypothesis is true in an independent samples t-test. What if we collect our data set and the mean of our first sample turns out to be 5, and the mean of our second sample turns out to be 2? Then we have a sample mean difference in our data set of 3. Which means our outcome, our data set is out here. And it looks like an extreme outcome. It looks like an extreme outcome in the situation where the null hypothesis is true. It doesn't look really very extreme in these other situations where the null is false and where the curve doesn't peak at 0. But it does look pretty extreme in this situation where the null is true. But once again, in order to know if this outcome really is extreme, we have to calculate a t-score, because we don't know how fast, without the t-score, we don't know how quickly this curve is dropping down. We don't know if the curve is still at a high point at 3 and doesn't really drop down far until you get to these higher numbers up here. So the t-score will be useful to tell us how extreme our outcome is. And just like in a one sample t-test, it tells us how many standard errors or estimated standard errors fit between the center value in our situation where the null is true, right here, and our outcome, or our data set, which had a sample mean difference of 3. If the t-score, so it's the t-score is the number of estimated standard errors between the center and our data set up here. If the t-score comes up to a high number, it means our outcome is at the extreme end of the curve. It means that a high t-score means that the curve is at a low point at our outcome, and we're in this narrow sliver at the right end of the curve. And once again, the t-score has to reach the critical value or higher in order for you to reject the null hypothesis. And if you do reject the null hypothesis, you're deciding that your outcome, or our data set, is so extreme in this situation right here, where the null is true, that we're going to reject the null hypothesis and say that this situation up here is false, and that one of these other situations is true, where the curve doesn't peak at 0, and where the two population means aren't equal. We're going to say that one of these other situations is true, where the difference between the two population means isn't 0, just meaning that the two population means aren't equal. So I hope this video was helpful. I just wanted to make this video as to help you understand some of the concepts that I talked about in some of my other videos, just in case they weren't completely clear.